Okay, welcome back to a new week with quantum computing. The topic this week is going to rotate around quantum gates and operations and quantum circuits and some simple quantum algorithms. We may not get to quantum Fourier transforms, but before we do that, I just wanted to remind you quickly of what we did last time with density matrices and the definition of entropy, which are topics which are extremely useful when we are going to analyze the concept of entanglement in quantum systems. This is also strongly related to the kind of measurements which we are going to do, and all the previous topics like the spectral decomposition of an operator, the Schmidt decomposition, the definition of a pure state and mixed states, and so on and so on. So let me quickly remind you of what we did last time. So I'm going to just bring up parts of the whiteboard notes. I haven't typed in the lecture notes from last week everything which we did. So let's switch back to the handwritten notes from last week, and let me remind you of some of the basic topics which we went through. So one of the things which we did last week was to discuss the trace of the density matrix. So let me just quickly remind you of that. So the first things which we did was to look back at the definition of the density matrix or density operator, where this P of I is a probability, and we know that the trace of the density matrix is equal to 1. And today we are going to play around a little bit with the density matrices first, before we switch over to the next topic, which deals with quantum gates and quantum circuits. And if you guys have the possibility next week, I would like to suggest that we extend a little bit the lectures, so that instead of having just 2 hours, we're going to run a kind of mini workshop where we also introduce the library developed by IBM, which is called Qiskit, which allows us to set up gates and circuits. So we're going to have a demonstration of Qiskit first, and then we're going to apply this to the kind of quantum mechanical systems which we will work on for the rest of the semester. So the trace is also a quantity which is invariant under transformation. So if we have a unitary transformation with a unitary matrix here, then we know that the trace is conserved. The topic which we also went through in more detail last week was now to look at a 2-qubit system or bipartite system, where we had a density matrix of a given system, and we use this one to define the partial trace of a given Hilbert space. So we could take and trace out one of the subsystems and obtain the density matrix for the system rho of alpha, which is called a reduced state or a marginal of a system A. So that means that we have actually a 2-body in this case, or 2-qubit system, and we produce the density matrix for a given state. So this could be the ground state or an excited state of a 2-qubit system or a 2-particle system. The system which we have been looking at is the system of 2 electrons, where each electron can be trapped in a harmonic oscillator trap. This is a kind of candidate system for making quantum gates and quantum circuits. And this kind of system is then actually a 2-body system, and we can define the density matrix with a given computational basis for that specific system. And based on that density matrix, we can then trace out the density matrix of one of the subsystems. And this is essentially what we spent some time last week on. So we can produce then a marginal of a system. And we looked at examples here where we had a Bell state, where we had a linear combination of qubits 0 and 1. This is an entangled state from the beginning. However, even if it's entangled, as we discussed last week, it is also called a pure state. It's called a pure state because it's exactly defined at the beginning, and then we can perform operations with measurements and so on this specific system. So even if it's an entangled system, which means that we cannot write it out as a product of single qubit states, A in system A and system B, it is a state which is still a pure state. And in this specific case, we use this kind of shorthand here, 0, 0 plus 1, 1. And we also reminded ourselves about the Schmidt decomposition. So this has a Schmidt rank D equal to 2 here. So it is an entangled state when we perform the Schmidt decomposition. And the states lambda 1 and lambda 2 here, when we sum up the probabilities, that sums up to equal to 1. So this is also one of the definition of the density matrix. And the density matrix for this specific state is now given by, when we now perform the operations here, we ended up with a matrix which looks like this. And then we went through the tracing out. So we could then find the density matrix for the marginal system or the subsystem. And this was done by setting up the identity matrix for that specific system we want to trace out. And we are tracing away system B. And this becomes a 4x2 vector or 4x2 matrix, which is more correct. And similarly, we had the one for the qubit 1 for system A. And then when we produce this tracing out of system B so that we are left with system A only, we ended up with the following density matrix, which we then could see was equal to 1/2 times the identity matrix. And then the trace of the matrix is equal to 1. The trace of the matrix squared is equal to 1/2. So this is less than 1, and that's used to define a so-called mixed state. And the trace of the matrix squared, if that is equal to 1, we say that we have a pure state. So these are definitions of mixed and pure states for the subsystems. So remember again that the total system A and B is not necessarily equal to the tensor product of the subsystems A and B. So the joint state of a 2-qubit entangled or not is a pure state. It is known exactly. However, when we were looking at the individual qubits, or for example, the entangled Bell state, then we found that they are in a mixed state. That means the following. We do not have the full knowledge of their states. So if it's a pure state, that means that we have an exact knowledge of the subsystems as well. So in this specific case with the Bell state, which is an entangled state, but it's still a pure state because we have specified it from the beginning that it is given by this combination of bits 0s and bits 1s. However, when we trace out the specific subsystems and we get the marginal density matrix for the subsystem, then we do not have the full knowledge of the specific substates in the subsystem. And that's why we would define this as a mixed state. If we have a perfect knowledge, then we call this a pure state. So just keep this in mind. We can start with a pure state, but when we trace out the subsystem, it means that the subsystem may not be in a pure state. And in our case, the subsystem is actually a linear combination of qubits 0 and 1. So we cannot specify it exactly in which one of it was. Then the other thing which we did last week was to look at the entropy. And we want to use the entropy as a measure of entanglement or pureness of the states, if you prefer. And entropy, in a way, measures your degree of unexpectedness. So the higher the degree of unexpectedness, the larger the entropy. So if you know exactly the state which you are in, that means it's what we normally would call a deterministic situation. You know that you are exactly in the ground state or you're exactly in a specific state, then the entropy should be equal to 0 because there is nothing unexpected. So one of the measures which was introduced in the beginning was actually something like the information content could be written as a log2 or just a log, base 10, for instance. That just gives a scaling factor of the probability. So this is the so-called Shannon entropy, is normally what is called the classical information entropy in a way which allows you to encode information in a very efficient way. So one of the nice properties of the probability is that when you take the log, it's actually additive if you have independent and identically distributed events. So this P here, they represent the probability of finding x1 and x2 given a domain of events uppercase letter X. And normally what is introduced is a better measure, which is normally the Shannon entropy, or which looks like the standard entropy, which are used from discussions of entropy in physics. And in this specific case, we know that when we take the limit epsilon goes to 0, this quantity is exactly equal to 0. Whereas when we take the limit or look at P of x equal to 0, here we get a divergence. And this is then reflected, obviously, in the diverging property here when P of x goes to 0. So a better measure is this quantity here, which you can think of as an expectation value of log2 of P of x. And if you take a binary system, this is a classic example, which you will find in basically all textbooks because you can do it easily analytically. And in this case, you have the probability of 0. You have two possible events, 0 and 1. It's a binary class of events. And then the probabilities have to sum to 1. So when you sum up these two probabilities, you get 1. And in this case, the entropy is given in terms of this function here, which is a concave function. So it means it has a maximum, and it has a maximum when we have a probability which is equal to 0.5, which means the highest degree of what we might call unexpectedness. Whereas when the probability is equal to 1, that means that we have a well-determined state, or 0, then the entropy is actually equal to 0. So the entropy is always larger than equal to 0, and in this case, it's a concave function. So that has many nice mathematical properties. So this x of x, when P of x is equal to 1, or P of x equal to 0, then there's no uncertainty. And we normally say that this is a deterministic observation because we know exactly in which kind of state the system is in. The quantum entropy is the analog to the classical entropy. And this is where the density matrix comes in, as we discussed last week. So you could now think of A be a quantum system that is prepared in a state, rho alpha, when we use the Schmidt decomposition. And this rho of alpha is a member of its Hilbert space. And the von Neumann entropy is then given as the trace of the density matrix. And the reason for that, for this specific definition, is actually that when we look at the spectral decomposition of a specific state in this subsystem A, then the density matrix can be rewritten in terms of the projection operator, which you have here, times the eigenvalue of the density matrix for that specific state. And this lambda j play the same role as probabilities, as we have discussed before. And the lambda j's are the eigenvalues, or the probabilities. And the states which you see here are the corresponding orthogonal eigenvectors. So rho alpha is a semi-positive definite matrix, and it's always diagonalizable. So this means that we can always find the eigenvalues, and with the eigenvalues, we can then use the properties that the log of the diagonal matrix is now given by the log of the diagonals, and these are the eigenvalues. So that means that when I take the trace of d of a, that is the same as a trace of eigenvalues. If I take the trace of the transform matrix here now, because the matrix is diagonalizable, then I can rewrite my trace as the sum over the eigenvalues, which are the probabilities, times the log of the eigenvalues, again, the probabilities. And this gives us the equation here, which is the quantum mechanical analog to the classical Shannon entropy, where you see here you have the probabilities and the log of the probabilities, and we have the same here. So if this S of A is equal to 0, that is in case the density matrix is a pure state. If S of A is larger than 0, we say we are in a mixed state. So this is kind of a measure of whether we have a pure state or not. So this was a repetition of what we did last week. So what I want to do now is actually to apply this to a kind of quantum system, which will be our first candidate system when we now, next week, are going to define the project which we will be working on for the rest of the semester. And next week, as I mentioned, we will also introduce Qiskit, and we will look at the simulation of some simpler quantum mechanical systems. So let's go back to the Jupyter notebook and take a close look at that and the simple example which I promised. So let's take a quick look at it. So the system which we are going to encounter first is a system which is based on this 2-qubit system. And we have each subsystem, A and B, has now computational basis states, which are given by qubit 0 or bit 0, as we often call them. And that is a spinor with elements 1 and 0. And then we have qubit 1 or bit 1, which is 0 and 1. Then we can construct a new orthogonal basis. So this single qubit orthogonal computational basis is orthogonal, and it's also normalized, as we have discussed earlier. And the subsystems could represent single particles or composite many-particle systems of a given system. As I said in the beginning of the course, you could think of every such subsystem as one electron, which is trapped in a, let's say, harmonic oscillator potential or some other type of confining potential. Or you could think of this qubit 0, bit 0 or bit 1, as the lowest lying state of a complicated many-body system. So one of the main problems when we are designing quantum computers with the existing technologies is that basically all these systems are complicated interacting quantum mechanical systems where we actually are trying to define a computational basis based on experimental information about the low-lying states of a system. So now we are just going to idealize this in the sense that every subsystem has now only 2 states, which are represented by bit 0 and bit 1. And then one of the things which we did in the very beginning of the semester was actually to define the many-body, or in this specific case, 2-qubit or 2-particle computational basis states. And these basis states here are, again, basis states which make up an orthogonal and normalized basis. So we have 0, 0, 0, 1, 1, 0, and 1, 1. So these are the computational basis states. Alternatively, you could have used the Bell states. These states, when we look at them, they are so-called pure states. We know exactly in which state the qubits are. So in both cases here, these are also product states, so they're not entangled states. Just keep that in mind. When we constructed the Bell states in the previous 2 weeks, then the Bell states were, from the very beginning, even if they are pure states, they are entangled states. These states are just plain product states, so they're not entangled. And these computational basis states, they're also going to define the eigenstates of a non-interacting Hamiltonian. So we are going to split the whole Hamiltonian in terms of 2 parts. We are going to have an interacting part, and we are going to have a non-interacting part. So that means that there is a part of the Hamiltonian which we can now split in terms of a term, H0, which has these states as eigenstates. So let me go back to the whiteboard and just try to clarify what we mean here, because this is going to be important in later studies when we are trying to understand what the computational basis means and why we sometimes choose a specific computational basis. So this is a computational basis. So keep that in mind. Nature may not be represented by this computational basis. It's a handy basis. So let me now try to explain a little bit more in detail what is coming up here. And I'm going to switch to the whiteboard so that we have a better way to understand what is going on. So what we are going to do now is to set up a simple Hamiltonian, which I'm going to rewrite in terms of a part H0, plus something which I'm going to call an interacting part. And I'm going to specify what I mean by this interacting part. So the interacting part may have diagonal matrix elements, and it may have non-diagonal matrix elements. I'm also going to define a computational basis. So let me remind you of what we had in the slides there. So this computational basis is now going to be given by this state 0, 0, where this one is actually the tensor product of qubit 0 in system A and qubit 0 in system B. And it becomes equal to this vector, which has 1, 0, 0, 0. Then I'm just going to state the other ones quickly. So these are the other states, 0, tensor product with a 1 of B, and this becomes equal to 0, 1, 0, 0. And then we have the next state, 1, 0, which is a tensor product of qubit A with qubit B in state 0. And this is 0, 0, 1, 0. So I'm trying to emphasize this linear algebra aspect because that makes it easier to see what is happening here. And this is a so-called, these states, they build up an orthogonal and normalized basis. 1, and then we have 1, 0, and 1, 1. So for those of you who may have taken a course in many-body physics, you know that it's often handy to find a basis where we can at least compute the eigenvalues of a part of the Hamiltonian in terms of analytical expressions. So what we are going to assume now is that the Hamiltonian matrix, or this H0 which we have, so when I act with this H0 on the state 0, 0, that is going to have an eigenvalue, epsilon 0. So the basis which we have chosen is an eigenbasis for parts of the Hamiltonian. And then we have H0 with 0, 1. We're just going to label this as epsilon 1. And then we have H0 acting on 1, 0. This is going to be epsilon 2 of 1, 0. So also when you're encoding this information, you could rewrite this in terms of a state 0. So you will often see this kind of notation. So this would be the second state. This would be the third state, where we start with 0. And 1, 1, which has its own eigenvalue, epsilon 3 of 1, 1. And this is normally just written out as a state 3 here, where we have encoded these states as a set of bit strings. And you see it's very straightforward to do that. You have 2 qubits, and you can easily, in the computer, you can encode these as simply as plain bit strings. Now, the thing which we are going to do next is to rewrite so we have rewritten the Hamiltonian, but we're going to use this as a computational basis. So the eigen states of H, the full Hamiltonian, H0 plus H1, they are not given by these eigenstates, but we can expand. If we use this as a computational basis, we can then expand the eigenstate, let's say for the lowest lying state, 0, that will contain an alpha 0 multiplied with 0, 0, plus an alpha 1. So these are the coefficients which we get from diagonalizing the problem. So we are going to set up a Hamiltonian matrix, which in this case is going to be a 4x4 Hamiltonian matrix. So we have this linear combination of states. So when we diagonalize the problem, we are ending up with a matrix, which is a 4x4 matrix. So we are going to have a Hamiltonian matrix, which now is going to contain matrix elements along here. So epsilon plus some lambda strength multiplied with some constant or some specific matrix element, which we're going to label as an HI 0, 0. There's going to be an HI 0, 1, an HI, so this is the interacting piece of the Hamiltonian, multiplied with a strength, lambda. And then we have a 1, 0, and then with the final element is an H1 multiplied with a strength, lambda. And we are going to define quickly now what this strength lambda is. So what I'm writing out now is a Hamiltonian as a function of a parameter lambda, where this lambda takes values between 0 and 1. So that means that when I put lambda equal to 0, I have no interaction. So it's going to be given by H0 plus lambda multiplied with this H of I. So here I'm going to have a lambda times the interacting piece of 1, 0, a lambda times the interacting piece of 2, 0, and finally lambda of HI of 3, 0. And this will have diagonal elements, and the final one is going to be epsilon 3 plus lambda of I, this interacting matrix element of 3, 3. And these matrices here are now going to be defined in the following way. So this lambda of H of I is something which I'm going to make pretty simple. It's going to be given by lambda of a Pauli matrix sigma x with sigma x, the tensor product, plus lambda and the Pauli matrix for Z with the tensor product of a Pauli matrix with Z. So the Pauli matrices, just to remind you quickly of that, sigma x is given by 0, 1, 1, 0, and sigma z is given by 1 and minus 1, 0, 0. So that's going to define my Hamiltonian matrix. This is just a simple model which I'm making up. Now, what happens, however, when you now look at this lowest lying state, just to give you an example, this psi 0 here, this is now going to be a function of this parameter lambda. So that means that what I will have now is an eigenvalue coefficient. These are actually the eigenvectors which result from diagonalization, which will depend on lambda, plus an alpha 1 of lambda of 0, 1, plus an alpha 2 of lambda of 1, 0, plus an alpha 3 of lambda of 1, 1. So that's going to be the combination of these different coefficients. And since I have a 4x4 matrix, there will also be 3 additional eigenvectors. So there will be a psi 1, psi 2, and psi 3. Any questions so far about this specific eigenvalue problem which we are setting up? So I'm now using the computational basis which I defined here as a basis which I'm going to expand the exact solution in. So psi 0 is an eigensolution of H, the full Hamiltonian. So when I take psi 0, that's going to give me an eigenvalue E0 of psi 0. There will be similar eigenvalues of psi 1, of V1, of psi 1, and then we will have an H of psi 2, which is equal to 2 times psi 2 here. And I'm skipping the bracket notation just of plain laziness of psi 3 here. So these are the eigenstates, the full eigenstates of the system. But I'm going to expand these in terms of the orthonormal basis, which I have defined, which is a basis which is an eigenbasis of a part of the Hamiltonian. Now, this is very useful in case the interaction is weak. So that means that we should now expect that when lambda is small, most likely then the lowest lying eigenvalue will be dominated by this alpha 0 term in case this epsilon 0 is well separated from epsilon 1 and epsilon 2 and epsilon 3. And just to remind you, epsilon 1s, epsilon 2 and 3, they are the eigenvalues of H0 with this specific computational basis. So this is just a choice we have made. And often this choice is a choice which is dictated by the physics of the system. So if the motion of a given system is well defined by, let's say, a harmonic oscillator type potential, and the interaction is weak, then this orthonormal basis which we have defined here could be a good approximation to the system. It's not going to give you the exact function, because the exact function is actually this one for the lowest lying state. And the depending on the strength of this parameter lambda, so when lambda is equal to 1, we have the full interaction. When lambda is 0, we have the so-called non-interacting system. So that means that what will happen is that these states here, depending on the strength of lambda, may be less dominant or more dominant. So if lambda is equal to 0, most likely then the ground state will be dominated by this term. For the second state, it will be this term here times an appropriate coefficient. But when we diagonalize the matrix and we bring in the interaction, make it stronger and stronger, there's going to be a stronger mixing between these different states. These states are still pure states, so you should keep that in mind. So when we now define the density matrix, we are now going to define the density matrix for a given state. So if we take a rho 0, that is the density matrix for psi 0. And that's the quantity which in the program, which we have in the Jupyter notebook, that is the type of density matrix which I'm going to define. And then I'm going to define a density matrix for this subsystem, which is now going to be a trace of over the subsystem B of the density matrix rho 0. So keep in mind that this is a density matrix which is now given by psi 0 for system AB. So you could now think of this as two subsystems as we have defined up here. Just let me quickly remind you. So the 0, 0 is now the tensor product of two subsystems defined by bits 0 and bit 1, so qubit 0 and qubit 1. So that means that the states which we are going to look at now is this marginal state here. You can show, as we also discussed last time, that this is equal to the tracing out of system A of the same density matrix rho 0. And then we can do the same exercise for excited states. So we could take the first excited state, this psi 1, and construct a corresponding density matrix, etc., etc. So the thing now is that if you look at this specific state which we have here, this one, with this basis, this is going to be a pure state because we have defined it. And as soon as we know the coefficients from diagonalization, we know exactly what is the linear combination here. So if we were to calculate the entropy of this specific density matrix, it would give us an entropy which is equal to 1. And that means that it's going to be a pure state because we know exactly what the combinations are. However, we do not know in which state the subsystem is. You can, what you're going to see now in the simulations is that if I have a non-interacting system like this one, then my state here will be dominated by this one. And then we know that the subsystem A is in qubit 0 and subsystem B is in qubit 0. So then the entropy should actually be equal to 0, because when entropy is equal to 0, it means that we have a pure state. The density matrix is equal to 1 if we have a pure state, and the entropy then is obviously equal to 0. So we are going to see this now when we look at the calculation of the density matrix for this specific system. And next week, we are going to look at how we can actually start encoding this using a library which is called Qiskit, which is IBM's library, which allows you to set up quantum gates and quantum circuits and perform simulations of these systems. And we will gradually use this to introduce the kind of calculations which we are going to do. So let me go back to the Jupyter notebook. So this is the background for the code, which you are going to see now, the results of. So let me just bring it up here. So we have defined the computational basis. Just a moment, let me click this away. So this is a computational basis, an orthogonal basis. And then I'm going to set up a Hamiltonian matrix, which is given by the tensor product of the 2 sigma x and 2 sigma z matrices. So this is just, keep in mind, this is just a model which I cooked up. There's nothing deeper than that. So it means that along the diagonal, I will now have an epsilon 0, 0, plus this interaction matrix element, which is going to be multiplied with a parameter lambda. And I have this new diagonal, epsilon 10, epsilon 1, 0, minus this hc, and then I have epsilon 0, 1 minus hc, and epsilon 1, 1. Actually, this should be 1, exactly. That's the way it should be. And then I have the non-diagonal ones, because if I only have diagonals, then there is no reason to diagonalize. So the non-diagonal parts are the parts which are going to mix the different states. If I don't have a diagonal part, then this is going to be pretty boring, because then I can just read off the eigenvalues. So what I'm going to look at, as I said in the handwritten notes, is a density matrix, which is now given by the first eigenstate, the one with the lowest energy. And we label this as psi 0. And that's simply given by the linear combination, where these alpha 0, 0, alpha 1, 0, etc., they are the eigenvectors of resulting from the diagonalizations. And they are normally called the eigenvector coefficients. And then we can set up the density matrix for the subsets, A or B. So we are tracing out B, which is now given by this specific density matrix plus this one. Or we can trace out the density matrix for the marginal state B. And these density matrices for the subsets can then be used to compute the so-called von Neumann entropy, which is one of the possible measures of entanglement. So a pure state has entropy equals 0, while the entangled states have entropy larger than 0. And this reflects this degree of unexpectedness. So if you're in a pure deterministic state, well known, then clearly your probability is equal to 1, and entropy has to be equal to 0. So the von Neumann entropy is simply given as a trace of the density matrices for the subsystems, either A or B. So what you will see now is that this example here shows the entropy based on the density matrix for the lowest many-body state. And you're going to see a jump in entropy as you increase the strength for the interaction. This is something which is reflected in what is called a, let me see, there's a, yeah, so there's a note in the chat here from Greg about the quantum computing. If you could give the link as well, I mean, that would be interesting here actually. So where you actually have, so I can also give you access to these IBM quantum computers. Actually, you can run for free on some of the selected machines. And we are going to discuss that next week, how you can set up a run on the IBM machines. So we can get some practice in implementing the specific gates. This is actually pretty straightforward. And we are actually going to discuss that in detail next week when we introduce Qiskit, how to run things on a quantum computer. But here, the interesting thing now is that when you look at this interaction strength, then when it's 0, we have many body states which are purely defined by their computational basis states. And as you switch on interaction, you obtain an increased degree of mixing, and the entropy increases till we reach something which is called a level crossing. So a level crossing means that the character of the ground state which we have, this specific state which we have chosen, it means that it switches character from being dominated by, let's say, 0, 0, to be dominated by one of these other states. And in quantum mechanics, this is often called for a level crossing. So actually, the levels don't cross, but what happens is that the character of the wave function changes. So by being dominated by a 0, 0, it can be dominated by a linear combination of the other states. And this is now going to give rise to an increased degree of mixing, which is then reflected in the calculations here. So you will now see that in the calculations, I'm actually setting up my non-diagonal part and the diagonal part. So I have a parameter lambda, which now spans from 0 to 1. And I put up 4 values. The dimensionality is 4 by 4. So this is sigma x. So this is the Pauli X matrix. And then this is the way you would now set up. So I have chosen a parameter h of x. And these are tuned so that the level crossing becomes more explicit. The matrix which I have is this one. So this is the sigma x with tensor product with sigma x. And that's given by this Cron or Kronecker operation. And then I have the same for the sigma z matrix. So I'm setting up the 2 matrices here. And then I just give the eigenvalues for the non-interacting case in terms of these matrices. So I set up the non-interacting part, I calculate the eigenvalues. And then when I have the eigenvalues, I'm calculating a Hamiltonian here, which is the eigenvalues will be given in terms of this lambda parameter, which is a strength for the interaction of these Pauli matrices plus the diagonal part. I diagonalize, as you can see here. I set up the eigenvalues and eigenvectors. I calculate the density matrix, which you can see here. This is the density matrix, and I'm picking the ground state. You can choose any of the other states. And in this case here, I pick the eigenstates of the lowest lying state, and I compute the outer product, so which is a density matrix. And then I'm setting up the projection of the density matrix for the subsystems. And this is now given by this projection operator, which we discussed last week. And it's multiplied with the density matrix and the projection transposed, as we discussed last week when we put up the equations on the whiteboard. And then I can do the same for the subsystem 2. And when I then set up the total density matrix for the subsystem, I have the subsystem for the state 1, 0, and then the state 0, 1. And by doing that, I get the total density matrix, the subsystem. And then I calculate the von Neumann entropy, which is then given by the trace. Or alternatively, I could take and diagonalize this density matrix, and I could take the trace of the eigenvalues of the density matrix. And what I'm plotting here are the eigenvalues of the system as a function of this parameter lambda. And then I plot also the entropy. So if you run this code, which is a first demonstration on this type of calculations here, what you will see now is if we now focus on the lowest lying state, this is the 2 body system or 2 qubit system. And what happens here is that in the beginning, the eigenstate is then dominated by the lowest line computational basis state, which has eigenvalue 0, and you can see that here. And then as we increase the strength of the interaction, this eigenvalue goes up. And then there is a change in the mixing of the state, so that it's no longer dominated by this state 0, 0, but it becomes a linear combination. And here what happens is that the state 0, 1 is the one which starts to dominate. So the wave function here changes character. And it's this change of character then which also leads to a entropy for the lowest, for one of the subsystems, based on the lowest lying state, where you see a clear jump in entropy. So here you have a pure state, and then gradually, as you increase the strength of the interaction and you have a stronger degree of mixing, you cannot tell in which state the subsystem is in, whether it's a state 0 or state 1. So in the beginning here, this is well defined by the qubit 0, but then as you start increasing the strength of the interaction, you can no longer tell in which state the subsystem is in. So the whole thing here is that you started with a pure state, which was given by the linear combination of these quantities. So if I were to calculate the von Neumann entropy for the ground state, which is here, if I were to do that, that would be a pure state because I know exactly the linear combinations here, and the entropy would have been 0. However, for the subsystem, I cannot tell now whether the subsystem is now in state 0 or state 1. And that is reflected in an entropy which is different from 0. So when I keep increasing the strength for the interaction, what you're seeing now is that when you increase the strength for the interaction, what happens is that the state of the system changes character, and it's going to be a mixed state, which then has a mixing of the different qubit combinations. And that is then reflected again in the subsystem, where we cannot define exactly what the subsystem, which state the subsystem is in. And that's given simply by this entropy here. Now, you may ask, what is the importance of this? The importance of this is that entanglement is, as we saw with the Bell states, is something which is an extremely useful property when we're now going to run quantum computations, because if a system is entangled, we can sometimes, by making a measurement on one of the subsystems, we can tell in which state the other system is in, without having performed a measurement on the other system. And we will see these things gradually as we start practicing. But this is our first encounter with the density matrix and the entropy, as we discussed last week, and as a measure of what we mean by a pure state and or a mixed state. So for the subsystem here, we started with a pure state for the many-body system, actually the two-particle system or the two-qubit system. And then as we switch on the strength for the interaction, we cannot tell in which of the subsystems, in which of the states the subsystem is in. Okay, I went a little bit over time, but I wanted to conclude this example here as a way to wrap up our discussions of density matrices and entropies, which are quantities which we will also use a lot in the future when it comes to discussions of measurements on quantum mechanical systems. Okay, so I'm going to stop the recording here, to pause the recording. So what we are going to do now is to set up quantum gates and quantum circuits, and also look at some simple algorithms. So this is going to continue next week and the week thereafter as well. So next week, I was hoping that we could have a kind of more extended session. So if it fits everybody, we could start at, let's say, 10 o'clock next Monday. And we could look at the introduction to Qiskit, and then we could continue with the discussions of the Hamiltonians to study and how we actually shape the project which we can work on. And so next week is going to be dedicated to the way we set up quantum gates and perform calculations. And then the Hamiltonian systems which we want to simulate. So what I wanted to start with now is just a quick reminder of some classical logic gates and circuits, and then point out that the classical gates are so-called irreversible and not invertible operations, which therefore cannot be used in quantum mechanics, because in quantum mechanics we are confined to use unitary operations. The thing which is interesting is that in classical computing, when we are setting up the kind of gates which can be used to perform computations, there is a set of gates which then can be used as universal gates to define all other operations. There is a similar quantum mechanical equivalent to classical gates, and we are going to look at these type of gates now. So what I will be doing now is just to switch back to the whiteboard, and then we are going to have a quick reminder on some classical gates and the type of operations which we have. And then we're going to remind ourselves for some of the basic 1-qubit gates. And then we're going to look at a famous gate, which is called a control NOT gate. And these are some of the basic operations in 1 and 2-qubit systems. The next time we are going to look at so-called 3-qubit gates, like the Fredkin and the Toffoli gates. These are also important gates, which you will encounter in software like Qiskit. So one other thing I wanted to say is that we have a textbook by Hunt, which we have recommended. This textbook allows you to actually go through and build up all the equivalent gates yourself. But this is going to be time consuming, and it can easily lead to work which corresponds to a master thesis. So we are going to strike a compromise between what we can achieve within 10 credits and what can be done without diving into all the details. If you want to write something like this yourself, it's going to take more time. And that's why we would like to introduce Qiskit, which is a very popular software, which interfaces with as well as the IBM machines and allows you to set up quantum gates and quantum circuits for quantum simulations. Okay, so let's switch back to the whiteboard and try to define some of these classic gates which you may have seen in different courses before. So let's just put this away. And we're just going to call this a new topic. So this is going to be classical gates. It's actually logic, often logic, gates, and circuits. So you have probably encountered something like a NOT gate, which we discussed in the beginning of the semester here. So the NOT gate is actually an example of a reversible operation, because knowing the output, we know what the input was. So the NOT gate is often just written like this. So you have an input, X, and you have an output, Y, and that has a so-called table here of incoming values and output values. So if I have 0, this gives 1, and I have 1 and 0. So this is as an example of what we call a reversible operation, in the sense that knowing Y, we know what the input was. However, if I take something like an XOR gate, which you may have seen before as well, so that has 2 inputs, X and Y. So this is a Y here, and it produces an output C. And in our case, depending on our input, we are going to get the following output. So X and Y are the inputs. So if I have 0, 0, this is given by 0. If I have 0, 1, this gives me 1. If I have 1, 0, this gives me 1. And if I have 1, 1, this gives me 0. And now you see that this is an operation which is not reversible, in the sense that if I know the output 0 here, I don't know whether I was in a state with x and y, or equal to 0, 0, or 1 and 1. Similarly, if I have output 1, I don't know whether x was in 0 or in 1. So this is an example of what we might call a irreversible and non-invertible operation, actually. And this is one of the hallmarks of, how to say, classical computations, which means that since we cannot determine the input for all possible combinations of input values, it means that there is also kind of loss of information when we are looking at the classical computations. So this is gate here is a so-called irreversible and non-invertible, or non-invertible. So clearly, if we wish to set up an equivalent of an XOR gate in quantum mechanics, we have to be a little bit careful, because quantum mechanics, all the operations have to be done by unitary transformations. The NOT gate is actually an example of a reversible gate. So this is actually reversible. But all the other classical gates which you may have encountered, so classical gates like the so-called the NAND gate, and I should also say that with a NAND gate and then NOT gate, you can actually construct all the basic operations which you can do with a classical computer. So the NAND gate is again a gate where we have an input X and an input Y, and an output C here. And the table looks like as follows. So we would have a 0, 0, and get 1. I have 0, 1, and get 1. I have 1, 0, and I get 1. And then I have, at the end, I have a 1, 1, which gives me a 1 here. Now you see again that sorry, it's not a 1, but it's actually a 0. So it's only in the case of a 0 as an output where you know the inputs, that they have to be equal to 1, 1. In all the other cases which you see here, you have a so-called non-invertible operation, which means that if you have an output which is equal to 1, you don't know whether x and y were 0, 0, or 0, 1, or 1, 0. So this is also an example of a non-invertible operation. And if you take many of the other type of gates which you have, like a NOR gate, an OR gate, and an AND gate, they are all examples of this. So the other types of gates, which I'm not going to list here, are gates like a NOR gate. You have the OR gate, and then you have the AND gate. So NAND is just not an AND gate. So that means that if you look at the table for the NAND gate, the AND gate is just the opposite of has the opposite outcome as a NAND gate. So these are all gates which are used in classical computations, but they cannot be used, except for the NOT gate, they cannot be used in quantum computations. So let's now go and look at the quantum computing gates. And the type of operations which we need to set up. So the typical things which we're going to do now is that we have an input-output state of an n-qubit system. So the input and output states are n-qubit states. Furthermore, what we have is that the qubit states which we have, they are computed as the tensor products of the corresponding state vectors of the individual input and output qubits. So if you have a 2-qubit gate, for instance, and just to give you an example here, a 2-qubit gate, that is normally constructed as a tensor product, where we have a qubit in the system A, which is now taken as a tensor product with the a qubit in system B. And these would be the input states. And then we would have corresponding output states from that. So typically what we end up using then for 1, 2, and 3 qubit operations, which are the cases which we're going to look at now, they will normally be constructed using these orthonormal basis states. So the ONB, or ONBs, since we are orthogonal and normalized basis states, for the analysis of these kind of, is going to be computed by take the 1 qubit gate. So we have the 1 qubit gates. We are going to use the states 0 and 1. And they are defined as specific 2 qubit Hilbert space. Then we have the 1 qubit space, which has 2 states. And then we have the 2 qubit gates. And then we are going to have these states 0, 0, 0, 1. We have 1, 0, and 1, 1. Now, when we then look at so we have actually 4 ONBs. And we've shown before that these states are orthogonal to each other. And then we have 3 qubit gates. In this case, we will have 8 vectors. And just to give you an example of one of them, 0, 0, 0 is going to be the tensor product for system A with a qubit in 0 in system B and a qubit 0 in system C. And in general, what we have then are the following states, which are orthogonal states. And we know that this state here is simply now a vector of length 8. So we have 1, and then we have 7 zeros. So that's that specific state. And it's easy to see that all the other states, we would have states like 0, 0, 1. There's going to be a 0, 1, 0. We will have a 0, 0, 0, 1, 1. And then we get a 1, 0, 0. We get a 1, 0, 1. We have a 1, 1, 0. And the final one, which is 1, 1, 1. And it's pretty easy to set them up. So these are the typical states and gates which we are going to look at now. And the way we're going to represent this, so suppose we have an initial state. So this can be an initial 1 qubit state, a 2 qubit state, and a 3 qubit state. So we have an initial state psi, and then we are going to get a output state when we perform these operations here. So we have an output state, which I'm going to call for phi. So what we have then is an operation of the type where we have a gate here. So this is an operator which acts on this initial state psi. And there are classical equivalents of the quantum gates, and these are the ones which we discussed just right now. But what we are going to look at now are, in particular, we are going to look at the 1 qubit gates. And we have already encountered some of these operations given by matrices like the Pauli matrices, the Hadamard matrix, and other ones. So we are going to look at 1 qubit gates G. We are going to look at the 2 qubit gate. There's a famous one which is important for all quantum mechanical computations, and it's called a controlled NOT gate. And this is going to be the so-called C-NOT gate, controlled NOT gate. And then we have 3 qubit gates, and those which we will encounter if we get time next week are the so-called Fredkin and Toffoli gates. Okay, so let's take a closer look at the 1-qubit gates. So 1-qubit gates, we have already encountered several of them. So in this specific case, these are 2x2 matrices. So we have an initial state, which is given by this state phi, psi as we defined it, which is going to be given by an alpha 0 or plus 0 plus an alpha 1 times qubit 1. And then we have our output state, which is going to be this state phi here, which is going to now be given by an alpha 0 prime times 0 plus an alpha 1 prime times qubit 1. And the matrices, which represent these gates, G, they are now going to be given by 2x2 matrices, where we have elements like G00, G01, G011, and then G11. So that's the basic structure of the operations which we have. So these matrices are going to be given by so-called invertible matrices. They're going to be unitary matrices. So what we have then is that G, so I'm putting hats on these, and G here is equal to the unit matrix. And this is also given by G times G. And this is multiplied with a self-adjoint here. So the matrix is invertible, and it has its inverse, which is also given by the self-adjoint matrix, is also a unitary matrix. So this implies that a quantum gate with a unitary transfer matrix can also be inverted. And this is extremely important since it shows that quantum gates are reversible, as opposed to classical gates, which are irreversible. So this is a very important aspect which we're going to look at. So when we've given this transfer matrix of a quantum gate and the input and the output qubits, what we have then is that the transformation which is performed by the gate, so this transformed state, is given now by G times this initial state psi. And that means that for a single qubit operation, we are going to get this new state, alpha prime, which is now given by this operation G00, G01, G10, and G11. And this is multiplied with alpha 0 and alpha 1. So when we now look at these different states here, what it means is that this alpha 0 is simply given by G00 times alpha 0 plus G01 times alpha 1. And similarly, I have alpha 1 prime, which is equal to G10 multiplied with alpha 0 plus G11 multiplied alpha 1. So the gates which we encountered, or the operations which we encountered before, are the following. So I'm just going to make a list here of some of the famous gates. So one is obviously called the identity gate. And that should be pretty trivial to set up. So that is given by 1, 1, 0, 0. So it just leaves a qubit unchanged. And then we have the the so-called X or NOT gate, which we have encountered, which is actually the sigma X gate. And that is given by the following matrix, 0, 1, 1, 0. So what it does, it changes qubit 0 to qubit 1 and qubit 1 to qubit 0. And so this has the exact operation corresponding to the classical gate, which is a NOT gate. So this has a classical, this is given by the classical NOT gate. Then we have other gates. So one is the so-called Y gate, and it multiplies the qubit by a complex number I and flips the two components. And this gate is now given by the sigma y matrix. So y is given by sigma y. So it flips the qubits and it multiplies them with a component I, the imaginary number here. And then we have the famous Z gate. And that changes or flips the sign of a qubit. So this actually changes the face. Actually flips the sign is a better way to say it, of a qubit. So perhaps flip the sign is a better way of saying it. And that's gate, the Z gate is actually the Pauli Z matrix, which is then given by 1, -1, 0, and 0. And then we had the other gate, the so-called Hadamard gate, which we encountered earlier, which is a very famous gate, which is widely used in quantum computations. So we have the Hadamard gate. And the Hadamard gate is interesting because that allows us to write our first simple quantum algorithm. So the Hadamard gate is given by h is equal to 1 divided by square root of 2, and it has 1, 1, 1, -1. And this is a gate which now allows us to actually write our first simple algorithm. Our first encounter simple algo with the Hadamard gate for random numbers. So how do we actually write this out? So suppose now that we have a qubit 0, which is our initial state. So we act with this Hadamard gate on an initially prepared state, 0. And that gives us a linear combination. So this is now a mixed state where we have 0 plus 1 divided by square root of 2 here. Now, what happens now is that when we measure, so upon a measurement, so we would prepare the state in a qubit 0, so we know exactly what it is in. And then we perform these Hadamard operations, which can be achieved by an appropriate setup of, let's say, electric fields, acting on lasers, acting on a specific qubit. And then on measurement, this state, the new state which we have, which is this mixed state, that will collapse to either 0 and 1. On measurement, the state will collapse to either 0 or 1. So that's the measurement. And the probability is the same with the same probability. Which is 1 divided by square root of 2 squared, which means 50%. So that means that if I look at this application of the Hadamard gate, then the probability amplitudes for each of the two possible resulting states, as I said, there's 1 divided by square root of 2. And that means that since we can construct one single completely random qubit, which we then can interpret as a classical bit after measurement, so we have a quantum mechanical state, which when we perform the measurement, produces now either bit 0, bit 1. We can then interpret that as a classical bit after the measurement. And if we are bundling multiple of these bits in parallel or sequence, that allows the generation of random numbers of any bit width. By random, we actually mean true in this case, atomic level randomness, which is not the same as the classical pseudo random numbers which we generate in standard algorithms, which are actually given by a deterministic algorithm. the so-called linear congruential methods, where you predict the next one with a certain probability, but where you have a deterministic algorithm to determine the next random numbers. So that means also that there is a finite, classically, there's a finite number of possible states in classical computers with a finite amount of memory. So that means that all random numbers which are generated on a classical computer are not truly random, and their sequence will actually repeat itself at a certain point. Whereas here, with the preparation of this atomic level type of randomness, there is the possibility to generate true random numbers. So if we can do this in parallel many times, we can then interpret each classical measurement here as a specific outcome, which is used then to generate a sequence of random numbers. So with this Hadamard gate, we could actually start making our first algorithm for setting up random numbers, actually. Now, the Hadamard gate has some interesting properties as well. And if we look at the Hadamard gate, so if we take this gate H, and we multiply it with itself, then it's easy to see that we have 1 over square root of 2. Then we have 1, 1, 1, minus 1 here. Let me just write this better. And then multiply with 1 over square root of 2, and then 1, 1, 1, minus 1. What we see is that this becomes simply equal to a half. And then we have 2, 0, 0, 2. And that's the same as the identity matrix. So that means that if I have a given state, a final state phi, and I operate with it two times with the Hadamard gate on initial state psi, this gives us back the identity matrix multiplied with psi, which is the same as the initial state. So that means that with the Hadamard gate, if we perform 2 operations with the Hadamard gate, I should be back to the state which I started with. And you can actually show that if you perform this many times, you have h times h, etc., times psi, and this is something like h to the power of 2k. So we have to do it twice at least to get this identity matrix. So it's in powers of 2. So this is the same as h of 2k multiplied with psi, and that's the same as the identity matrix, power of k, and that's nothing but just the state itself. So if we have n equal to 2k plus 1, then what we get is actually just the Hadamard matrix multiplied with the state psi. So that is also a very useful operation here. So that means if we just rewrite it, psi of a, which is equal to h to the power of 2k plus 1, this is just the same as h times psi. Now, the next gate which we're going to look at now, after we've done this 1-qubit gate, is a very important gate, and that's the so-called C0 gate. And we are going to spend some time now, but also next week, on discussing the C0 gate. And because the C0 gate, together with the NOT gate, they form the central gates in quantum computations, which can be used to basically build up all other operations. So let's now look at the 2-qubit gate. And the important gate here is the so-called C0 gate. So let's now look at the specific state which we have. So the input and the output qubits of a C0 gate, they can be represented as a vector in 4-dimensional space. So we would now have these basis states 0, 0, 0, 1, 1, 0, and 1, 1. So it means that the input gate is going to be given by the following. So we would now have something like a typical input state that can be represented by the tensor product of two states. So psi with phi with psi. And in this specific case, what this is a state alpha 0, alpha 1, and then the cross product with a new state, which is beta 0 and beta 1. So that would be the typical input state, because now we're dealing with 2 qubit gates. And what we have now is a state phi, which is given by this linear combination alpha 0 plus alpha 1. That's why we are writing it out in this compact way. And then we have the state psi, which is given by beta 0 times 0 plus beta 1 times 1 here. So these are the two states for the single qubits, which are then tensor producted with each other to produce a new state. So the new state which we have is now going to be given by the following vector. So I have an alpha 0, beta 0. I have an alpha 0 multiplied with beta 1. So I'm just taking the tensor product. So let me just rewrite it a little bit. And then I have an alpha 1 with beta 0 and alpha 1 with beta 1. So that's the tensor product of these two states, phi with psi here. So that could be the input state. And the way we are going to set this up now is in the following way. So we're also going to make a drawing. So we would have a something which we are going to call a control input X. And then I have a target input, which I call for Y. And the way we're going to mark this now is that the control input X is now represented by this circle here. And that produces an X here. And then I have the target input, which I'm going to mark with this plus here. So this is actually the addition of the qubits with modulo 2. So this is going to be given by X and modulus 2. So the addition plus and modulo 2. So this operation here is the same as addition and modulo 2 here. Now, if I take my states, which I'm preparing, so I'm going to have a state which I call psi here, and that is sent into the system. And it's called a control input because we end up with the same state, psi. And then I have the target input, which is the state phi here, which is going to be the same as a tensor product of, no, the model of the two, and I'm going to write this one as a psi of phi here. And this is now marked like this and like this. So this is the way we are going to define this gate graphically. And the components of the input vectors, they are transformed by the C0 gate as follows. So the components in this basis, which we have, the components, we want them to transform as follows of the input vector. So remember now that when I write something like 0, 0, this is actually the tensor product of bit 0 for one of the systems and bit 0 for the other system. So this is going to be unchanged, 0, 0. I'm going to have a bit 0, 1. That's also going to be unchanged. But then I have bit 1, 0. And in that case, this is going to change to 1, 1. And then I have the 1, 1 here, which is going to change to 1, 0. So the classical equivalent of the gate, which you see here now, is the same as the XOR gate. So the operation here has a classical equivalent. Is the XOR gate. Just to give you an example or quickly remind you of what the XOR gate is. So let's just look at the table for that one. So the XOR gate has the following table. So we have this X, Y, and Z, which we discussed a little bit earlier today. So we have an input 0, 0, and that produces 0. I have an input 0, 1, that produces 0. I have an input 1, 0, which produces 0. And then I have this, no, sorry. I was looking at my wrong notes here. So 0, 1 produces 1. And 1, 0 produces 1. And then when I have 1, 1 here, that produces 0. So if you look a little bit closer here, you can see now a kind of equivalent here, because I have 0, 1 that produces 0, 1. So these are the two qubits. So one stays 0 and the other stays 1. So which is the number here I want. And then when I do 1, 0 here, I get 1, 1. So I have one of them outputs 1. And then when I have 1, 1 here, which will be the same as this one, I get 1, 0, where this 0 here corresponds to the same thing which you see here. So the so-called C0 gate has a classical equivalent, which is the XOR gate. So its output is the sum modulo 2 of its two inputs. And for a classical C0 gate, the target output is equal to the target input if the control input is 0 and flipped, if the control input is 1. So this quantum C0 gate, so you can actually define a classical C0 gate, but the quantum C0 gate has actually the same two inputs, and the control input is a qubit in a specific state, and the target input is a qubit in the other state. And the operation of the C0 gate is informally described by you having the control input is transferred directly to the control output of the gate, and the target output is equal to the target input if the control input is 0, and it is flipped if the control input is 1. So you get the same type of operations which you would get if you were to use an XOR gate. So the way we can now construct this is to set up a gate, which now is given as follows. So the gate which performs this operation, so the C0 gate, is now something which is going to be given by the following matrix. So it can be written as a sum of the outer products of the components of the output and input vectors. So the gate here, and I'm going to mark this with C0, is now going to be given by 0, 0 with 0, 0. This is the inputs and the outputs. So I'm actually going to write the gate as the sum of the outer products of the components of the output and input vectors. Then I have the next one, which is now a 0, 1 and 0, 1 plus, and then I have a 1, 1, which gives me a 1, 0, plus the final one, which is 1, 0 with a 1, 1. So if we now look at the way this matrix is going to look like, if we now perform the operations, then we are going to get a gate which looks like as follows. When we perform this tensor products, no, sorry, the outer products, we are going to get a gate which looks like 1, 0, 0, 0, 0, 1, 0, 0. And then we have 0, lots of zeros here, 1, and then we have 0, 1, 0 here. And this is actually put together with a unit vector, now unit matrix for the upper block here. So this upper block is just a unit matrix, and the lower block is actually a CX gate, or just an X gate. So we can now, if we now look at the output states, given the input states, we can now perform these operations. And I see that my time is running. I'm running over time here. So next week, we are going to look at how we can implement these gates. I'm going to add some more mathematics to this. And we're also going to look at other gates like the 3-qubit gates, the Toffoli gates and the Fredkin gates, which are important gates. And this is something, these kind of basic constituents here are some of the basic gates which are involved in quantum computations and which can be easily rewritten using a software like Qiskit, which allows us to program these gates pretty easily. So I'm going to continue next week and link this up with Qiskit, and then hopefully we can start looking at some of our first quantum simulations here, and then really get started with some serious work. But this is going to stop my lecture today, and then we will just continue with this material next week, and hopefully we can have an extended session if it fits everybody. I will mail you all about that.